space often feels empty, quiet, and still. When we look up at the night sky, it gives the impression of something calm and unchanging. But hidden within that stillness are some of the most extreme objects in the universe. Places where the very structure of space and time begins to break down. Tonight, we are going to explore one of those objects. Not through dramatic claims or fast explanations, but slowly, piece by piece, so the idea can settle into place. Black holes. To begin, it helps to set aside the common image most people carry. Black holes are often imagined as cosmic vacuum cleaners, pulling in everything around them, swallowing entire regions of space without limit. But that picture, while dramatic, is not quite accurate. A black hole is not a thing in the usual sense. It is not a solid object, nor a hole in space like an empty tunnel. Instead, it is a region where gravity has become so strong that nothing, not even light, can escape once it crosses a certain boundary. That boundary is known as the event horizon. From the outside, the event horizon appears calm and perfectly defined. There is no visible surface, no edge you could touch, but it marks a very real limit. Once something passes this boundary, it can no longer return. Not because it is being pulled back like an object on a rope, but because all possible paths through space and time now lead inward. To understand how this happens, we need to step back and consider gravity itself. In everyday life, gravity feels simple. Objects fall toward the ground. Planets orbit stars. But in modern physics, gravity is not just a force pulling things together. It is a bending of space and time. Mass tells space how to curve, and curved space tells matter how to move. Most objects, planets, stars, even entire galaxies, create only gentle curves. Light can still travel outward. Objects can escape if they move fast enough. But if enough mass is compressed into a small enough region, the curvature becomes extreme. At that point, something unusual happens. The escape velocity, the speed required to move away from the object, exceeds the speed of light. And since nothing can travel faster than light, nothing can escape. This is the condition that defines a black hole. What remains is not a surface, not a structure, but a region where all paths lead inward. From the outside, it appears as a perfectly dark sphere, often surrounded by a glowing disk of material slowly spiraling inward. This disk, known as an accretion disk, can become incredibly bright as matter heats up to extreme temperatures, but the black hole itself remains unseen. At its center, according to current theory, lies something called a singularity, a point where density becomes infinite, and the known laws of physics no longer function in a predictable way. It is important to pause here. The singularity is not something we fully understand. It is not a confirmed physical object in the usual sense. Instead, it is a sign that our current models have reached their limit. The mathematics points to it, but the true nature of what exists at the center remains unknown. In that sense, black holes are not just objects. They are boundaries of knowledge. Now imagine approaching one. From a distance, nothing seems unusual. If the black hole has the same mass as a star, its gravitational pull at a distance would feel no different than that star. Planets could orbit it in the same way. Light would move normally. It is only when you get close that the differences begin to appear. As you approach the event horizon, time itself begins to behave differently. To an outside observer, your movement would appear to slow down. Your signals would stretch, becoming redder and fainter. Eventually, it would seem as though you freeze in place, never quite crossing the boundary. But from your own perspective, nothing unusual happens at that exact moment. You would pass the event horizon without noticing a specific edge. There is no surface, no sudden impact, just a quiet crossing into a region where escape is no longer possible. Beyond that point, the path inward becomes unavoidable. This leads to one of the most fascinating aspects of black holes, the way they reshape the meaning of direction. Outside a black hole, you can choose to move forward, backward, left, or right. Inside, all directions point toward the center. Moving forward in time becomes the same as moving deeper inward. It is not that something is pulling you in. It is that the structure of space-time itself is guiding you there. Over time, tidal forces would begin to stretch you. The difference in gravity between your feet and your head would grow stronger and stronger. This process, sometimes called spaghettification, would eventually overcome any material structure. But again, this is not a sudden event. It depends on the size of the black hole. In very large black holes, you could pass the event horizon without immediately feeling extreme forces. The stretching would occur much later, deeper inside. This quiet progression is part of what makes black holes so difficult to intuitively understand. They are not explosive or chaotic at the boundary. They are calm, almost silent. Now, there is another layer to this story, one that connects black holes to quantum physics. In the 1970s, physicist Stephen Hawking proposed that black holes are not entirely black. Due to quantum effects near the event horizon, they can emit a very small amount of radiation. Over incredibly long periods of time, this radiation could cause a black hole to slowly lose mass and eventually evaporate. This idea introduces a deep puzzle. If a black hole can disappear, what happens to the information contained within everything that fell into it? In physics, information is not supposed to be destroyed. The fundamental laws suggest that it should always be preserved in some form. But black holes seem to challenge that principle. This is known as the black hole information paradox. It remains unresolved. And so, black holes sit at the intersection of two major theories: general relativity, which describes gravity and large-scale structure, and quantum mechanics, which describes the smallest scales of reality. Each theory works extremely well on its own, but inside a black hole, they come into conflict. This is one of the reasons black holes are so important. Not because of their dramatic appearance, but because they reveal the limits of our understanding. They show us where our models stop working. They quietly point toward something deeper that we have not yet discovered. And yet, despite all of this, black holes are not rare. They are a natural outcome of stellar evolution. When very massive stars reach the end of their lives, they can collapse under their own gravity, forming black holes as a final state. There are also supermassive black holes, millions or billions of times the mass of the Sun, sitting at the centers of galaxies, including our own. These objects are not anomalies. They are part of the structure of the universe, which brings us back to where we began. A quiet sky, a sense of emptiness, and hidden within it, regions where space and time fold inward, where the familiar rules no longer apply, where our understanding reaches its edge. Black holes are not just distant objects. They are reminders that the universe is deeper than it appears, and that even in stillness, there are layers of complexity waiting to be uncovered.